In our previous videos, we've been looking at the unloaded potential divider. And when we're looking at the unloaded potential divider, this is exactly how it looks like. We are having a source of EMF, a cell which is having like 12 volts, and this 12 volts is being distributed amidst these two resistors. Since these ones are identical, these 12 volts with a negligible internal resistance means that it's having 6 volts here and 6 volts there. And the output voltage, the one that was required or the one that is required, does not have any load on it. Now, that is as of what we've been doing previously. Now, when we are talking about a loaded potential divider, we are talking of one whereby when we are the portion where we are requiring the voltage output, there is a load. Looking at that illustration, for example, we are having a diagram, a circuit diagram, just similar to one before, but the output voltage, or the portion where we're being told to find the output voltage, there is a load. So we are having a load of 5 ohms that is connected to this portion of the circuit, and so this qualifies it to be a loaded potential divider. So in this circuit diagram, we are going to find the voltage output at this terminal. The procedures will be like we've been doing before. We are going to first have to find the current that is going through, that is being produced here. So, and then of course we know that the potential difference across that resistor is the same as the potential difference across that resistor, and definitely it is the potential difference at the output terminals right there. So if we may start to find the amount of current that is flowing through this entire circuit, it means that the current flowing, let's call it IS, the current flowing from the source is going to be equal to the potential difference, which is V, over the effective resistance R. Now, of course, the V, which is the EMF V, which is 12, divide that by the effective resistance in the whole circuit. Now, to find the effective resistance in the whole circuit, we have this combination and then that combination. So this is a parallel combination, then this parallel combination is in series with this. So to find the effective resistance means we're going to first find the effective resistance across the parallel combination, and in this case the resistance there across here, it's going to be times 5 over 5 plus 5, which is going to be 25 over 10, giving us 2.5 ohms. So it means that the effective resistance across that combination is 2.5 ohms. So if the effective resistance across this combination is 2.5 ohms, it means our diagram can be remodeled to look like this. So this is the 2.5 ohms we're talking about, the effective resistance across that combination. Now this effective resistance is in series with that resistor. So it means that the effective resistance in this circuit, if we continue with our calculation, will mean that the effective resistance will be 2.5 ohms plus 5 ohms, giving us 7.5 ohms. So 7.5 ohms is the effective resistance in this whole circuit. So to go ahead and find our current flowing is going to be equal to V over the effective resistance. Our V is 12, divide that by the effective resistance, which is 7.5, and therefore the current that is flowing through this circuit is 1.6 amperes. So we have 1.6 amperes being produced here. So meaning to go ahead and find the voltage output right there, we shall say that the voltage output is going to be the current flowing through this times R. In this case, the current flowing is what we got here as 1.6. Multiply that by the effective resistance across that combination, which is 2.5, and definitely our answer there is 4 volts. So 4 volts is the output voltage at these terminals. Now in the just concluded worked example, we've been using resistors of fixed resistances. However, we can introduce a slide wire. With a slide wire, it means that the voltage output can always be regulated by sliding the wire across the length. So meaning that if we get this wire and slide it across here, this is a potential divider, it is having 10 ohms. And when we slide this wire across here, it means we are regulating the resistance of this. If this is our cell, for example, we know that current is flowing in that direction, and if that slide wire is, let's say, if this is halfway and this portion is halfway, it means that current will come and only flow like that, leaving this other part redundant. So meaning that if this thing is 10 ohms, if this slide wire is halfway, it means this is 5 ohms and that is 5 ohms. And if we are to remodel this or to redraw this circuit, it would mean that current is flowing out, and since this thing is at the center and it's only going through 5 ohms, so this is like, it's like drawing it like this, that current is going through the 5 ohm resistor and this other part is redundant. Now this is what we've been doing previously when we're dealing with unloaded potential dividers. Now it's going to be the same case even when we are dealing with loaded potential dividers. Right there we are having a potential, a slide wire, and we have decided to put this in the middle of this slide wire. Let's say this slide wire has 10 ohms as its total resistance for the entire length. So meaning that if we put that wire there in the middle, this would mean that this is 5 ohms and this is also 5 ohms, because the whole of this thing is 10 ohms. So as current is flowing through, coming through the whole slide wire, and then we decide to put some wires there to tap it off, and probably we load it, we put a load here, let's say 5 ohms still. It would mean this, remodeling this diagram is the same as drawing it like this, and here we're having 5 ohms, then the other 5 ohms is right there, and that is 5 ohms. Now in most cases we remodel the diagram or we redraw it for easy understanding, and we normally do this when we are at the beginning stages, but of course as you get used to these kinds of diagrams, it's not necessary to remodel it like this. It's always obvious. You just go on straight forward with the calculation. So for this case, we will do a worked example to illustrate this further. A battery of EMF 15 volts is connected across a potential divider. This is the potential divider they're talking about, of resistors 600 ohms. So these are the 600 ohms of the potential divider, or called the slide wire. A load of 100 ohms is connected across the terminal of the potential. So this is the load they're talking about, and it is connected across the terminal of this. Of course, this wire can be slid along that to regulate the resistance. So a load of 100 ohms is connected across the terminal of the potential divider as shown. If the slider is halfway the divider, find the PD across the load. Now, of course, if this slider is halfway this divider, and this whole thing is 600 ohms. If it is halfway, it means that this portion is 300 ohms, and this other portion is also 300 ohms. This is coming from the fact that the resistance of a conductor is directly proportional to the length. The longer the length, the higher the resistance. The shorter the length, the smaller the resistance. So still, if we are to remodel this diagram to draw it again so that it makes more sense for some of us that are just looking at this for the first time, this is how it would look like. It would look like this. We're having the 15 ohms right there. This is the 16 ohms, but since the slide wire is in the middle, so this portion is 300 ohms right there, and then this other is also 300 ohms. Then we have 100 ohms, which is the load that is put across, that is in parallel with this, which is right here. We have 300 right there, and then 100 ohm load right there. So in this question, we are being told to find the PD across the load. So we are supposed to find the PD across the load. Of course, finding the PD across the load, again, we need to first find the current that is coming through from here, going through. And of course, finding the current means current is going to be equal to voltage over the effective resistance in the whole circuit. Now the total voltage in the whole circuit so happens to be 15 volts. Divide that by the effective resistance in the whole circuit. Now the effective resistance in the whole circuit is a combination of this and that. Now to first find the effective resistance, let's get the effective resistance of this parallel combination. We know that the resistance of that parallel combination is going to be 300 times 100. Divide that by 300 plus 100. That's going to give us, divide that by 400. So we have 300 over 4 ohms, and this is the effective resistance across that combination. So meaning that if we are to since we have the effective resistance across that combination, we remodel our diagram and it looks like this now. So this parallel combination has been fused into one big resistor, which is 300 over 4, and so this now is in series with that one. So we go ahead and find the effective resistance further by adding those two resistors. So it means the effective resistance R is going to be equal to 300 plus 300 over 4, and definitely there we will end up with, now that we have the effective resistance in the circuit, we can go ahead and find the current flowing through the circuit. From V is equal to IR, we know that I is equal to V over R. That's going to be the V, which is 15, divide that by the effective resistance, which is 375, and we shall end up with the amount of current flowing through the circuit being 0.04 amperes. So it is 0.04 amperes. So now that we have 0.04 amperes as the current, so we can go ahead and find the output voltage right there. The output voltage will be V0 is going to be equal to I times R, which is going to be the current, which we got there as 0.04, multiply that by the resistance across the potential difference across the load, which is 300 over 4, and we will end up with.
This brings us to the end of this video. Thanks for watching. Feel free to check out other excellent videos on the channel, and don't forget to subscribe. For Kisembo Academy, this is Arnold Rangakuramia helping you manifest excellence.